Welcome everyone. So this is a quick slide about who I am, so you can find me on the web under different silly nicknames. As was just mentioned, I'm one of the co-organizers of the C++ user group in Munich. So if you ever happen to be in or around Munich, be sure to give us a call and visit one of our meetings. And in my day job, I'm currently working for BMW as a software architect for the autonomous driving platform. So let's talk about Lua. So can I maybe get a quick show of hands? Who of you has used Lua before in a project of theirs? Okay, yeah, that's actually, wow, quite a few hands. I hope I won't bore you too much because this talk is meant more as an introduction to Lua, explain to you a little bit what the language is about, why it might be a good fit for your project, and then we will also look at how you can integrate it with a C++ application. Because one of the unique things about Lua is that it's actually not a standalone scripting language like Python. It was designed as an embeddable language. That means you typically use it within a larger program that was written in another programming language, often C++, and then you simply have parts of your program code written in Lua. And of course, Lua is most famous for its use in games, so its history is undoubtedly connected to gaming. So who remembers this? Yeah, couple of hands. So I'm German. That means I spent a considerable amount of my childhood playing point-and-click adventure games. And I played this countless times. And I don't know how well you can read it, but the sign over the door there actually says Scum Bar. That's scum with two M's, S-C-U-M-M. Does anybody here know what scum stands for? Anyone? No one. Okay, so not enough Germans in the audience, I guess. So SCUM is short for Scripting Utility for Maniac Mansion, and that is actually the in-house scripting language that was used at Lucasfilm Games to create their 2D point-and-click adventure games. And in case you didn't recognize it, this is actually the first Monkey Island game, The Secret of Monkey Island, which was released in 1990. And the scripting language has been around since Maniac Mansion. That's how it got its name. And it has been used in all of the 2D classic LucasArts adventure games. And this is actually like sort of an inside joke calling out to that language. But now, what you might also know is that in the late 90s, actually, LucasArts stopped making 2D point-and-click adventure games and transitioned towards 3D point-and-click adventure games. And the reason why this is related to Lua is that Lua actually was a project that was being developed at a university in Rio de Janeiro in Brazil. And for political reasons, in Brazil, it was very difficult during the early 90s to use software projects that were not being developed in Brazil. So Lua was born sort of out of a necessity that they could not use any of the mainstream programming languages, so they had to write their own. But of course, also, this language wasn't very well known outside of Brazil. Until an article in Dr. Dobbs' journal, which was a magazine for programmers back in the days when magazines still came on paper, in 1996 about Lua. And this article by itself did not generate a lot of a fuss, but it was read by one man, Brad Magalowski, who was at the time the lead programmer for Grim Fandango, which was actually the first 3D point-and-click adventure made by LucasArts. And they were at that point in time, which was like 1996, had the problem that their existing scripting language, SCUM, did not work very well for the 3D use cases. So they now had to make the decision whether they would adapt their in-house technology and somehow make it work with 3D, or use an existing language for solving that problem. And they eventually, because of that article, decided to go with Lua. And then Brad gave a talk at GDC about how they used Lua in Grim Fandango, and that basically was the start of Lua's success story in the games industry, and from there on it spread into various other industries. So as we can see here, this is the 4th Monkey Island game, Escape from Monkey Island in 2000. This was in 3D, and there is a Lua bar in here. So that's the connection here. Of course, you can also these days find Lua in lots of other applications, like World of Warcraft was already mentioned in the introduction, which is probably one of its most famous use cases. Adobe Lightroom is written to a large degree in Lua. There's also Love, which is a 2D game engine that is entirely programmable in Lua, which is very nice to use for game jams and small games. But it's also curiously used a lot in embedded software, in particular for Maker Project. This here shows one of the Node MCU controllers, which is an Arduino-based controller that is very, very popular these days, and you can program these devices fully in Lua. So the most distinct thing about Lua is probably its size. So you're not supposed to be able to read everything that is here on the left side, but what this is actually the complete syntax of the language in eBNF, and it nicely fits on a single sheet of A4 paper. The compiled binary of Lua, the compiled Linux binary, is under 180K in size, and that actually contains the full Lua package, including all standard libraries. You can reduce that size considerably by removing libraries or removing the parser if you only ever need to execute from bytecode. The reference manual is only 82 pages, and that actually includes the complete reference for the complete language, all the standard libraries, and the complete C API. There's only 8 basic data types in Lua. So from all of these numbers, you can probably guess that it's a very, very reduced set that ships with the language, sort of the opposite of what you would get with Python and its batteries included philosophy. Lua is very much batteries not included. It only includes the bare essentials and nothing more than that. And the point of this talk is sort of to convince you that this is not so much a limitation for Lua as it is a virtue. They actually try to make the best out of being small, and their whole design philosophy, the whole way that the language works, is built on that principle that being small can be an advantage, actually. Not only because you're able to run on platforms where bigger languages cannot run, like the embedded example that we saw before, but that it can really result in quite some beautiful language design decisions. So whenever you see some code examples later on from Lua, that is actually the motivation behind them is actually to show how Lua achieves certain things without adding burdens to the language. The language comes with a very few but very powerful language concepts, and then is the way that those concepts get assembled, how they work together, that actually allows you to model really, really powerful things. This is the way that I like to summarize it is the whole language fits into your head at the same time. Okay, which is something that I cannot say of almost any other language. I certainly cannot say this about C++. Like with C++, you can only keep a small subset in your head at the same time, and then you need to constantly swap it in or out depending on what you're doing. So with C++, there's no way to fit everything in your head at once, unless maybe you're one of those guys then. Okay. One last disclaimer before we get started. For a talk like this, I have to assume that you have never used Lua before, but I still want to show examples that are somewhat interesting, which might at some point lead to situations where an example might seem overly complicated or contrived or artificial. If that happens, please do not blame that on the language, but blame that on the talk. With that out of the way, this is Hello World in Lua. Simple enough. Please note that my syntax highlighter likes to make the print function blue because it comes from the standard library. That actually does not mean anything special. It's just a function like any other, and we will see the implications of that very soon. So this is a function in Lua. As you notice, we can have multiple arguments and we can have multiple return values for functions. We usually invoke a function like this, but Lua is actually, like most scripting languages, not very strict on its syntax. So, for example, I can just specify less return values and then it will still work. It will just discard the additional return values. I can even leave out some of the arguments and then the function call will still work. The function will just not get any valid values for these arguments. And if the function is prepared to deal with that, then this will just work. So you get stuff like optional arguments basically for free from this fact. Another interesting property of functions is that all functions in Lua are lambdas. So what that means is that if we see a function declaration like this, that is actually just syntactic sugar for this. And this might look a little strange, but what this actually does is you have an anonymous function that takes 3 parameters and does something with them. And then this function is a value in Lua. It's a value of function type. And now you assign this value to a variable of name f. This is not in any way different from any other kind of value assignment. You could also assign a number to f. That would be just the same. So functions in this sense are really true first-class values in Lua. They just behave like strings or numbers or anything else. You can, of course, invoke them. That's the property of the type, that you can invoke them with the parentheses, like do a function call. But other than that, the way that they interact with variables, with names, is the same as for any other values. And this goes back to what I said in the beginning, that Lua is small. There's only very few distinct concepts. So there is no separate concepts for functions that have names, right? We just reuse the mechanism that we already have in place for values and then just say, okay, a function is just one specific type of value. But other than that, it works exactly the same as for integers, so we can reuse a lot of the mechanisms that we already have for those. So a consequence of this is that replacing functions is trivial. So if I don't like the print function that comes with the standard library, I can just assign a different function and then print through that. One use case why I might want to do that is, for example, what if I want to count the number of invocations of the print function? Then I can just basically install a function hook. So I save the original print function into a variable, and then I replace the print function in the global environment by a new function that increments the count and then forwards the call to the original print function. What is not so nice about this example is we are using global variables here. So notice that there are no variable declarations anywhere in this code. But if I just assign to an identifier that has not been declared before, then Lua will just assume that this is a global variable. So these first 2 lines here actually create 2 new global variables named count and old print. And of course, like a lot of scripting languages work this way, and it's not that nice because you can accidentally introduce global variables even though you did not mean to. But the bigger problem right now is going to be that we don't actually want to pollute our global namespace with a variable named count. Like, this is just not good code hygiene. So what we want to do instead is hide those variables inside a more restrictive scope. The main tool that Lua gives us here is just using local variables. So the way that we are going to do the function hooking now is we are going to introduce a function that will perform the hooking for us. And now our variables are going to be local variables inside that function. So if I declare a variable with the local keyword, that actually restricts its scope. In this case, to the lifetime of the function. And now if I do the same thing as I did before to perform the hooking, then the referring to count and old print inside the new print function actually refers to those local variables in the enclosing scope. As you might notice, if you're familiar with lambdas, this now actually means that those local variables have to be captured so that they are visible inside this inner print function. And in C++, we do the capturing explicitly by writing it inside these array brackets, inside the capture list for the lambda. In Lua, it just works out of the box implicitly. But you might notice that we do have a problem now, because our count is now a local variable. So if I now actually want to check how often the print function was called, how do I read this count again, right? I mean, it goes out of scope as soon as I leave my enable counting function. So how can I access this again? So I just return a function that gives me back the count, okay? And so whoever calls enable counting would save this function that is returned from the enable counting call and then can invoke that whenever he wants to get back the current value of the count. And this might seem magical to you, especially if you are familiar with lambda captures in other languages, because what happens now is that the count variable, which is just a number, which means it has value semantics, is now actually captured by two different functions, and they're able to, they always see the same count, so they synchronize the changes on these values. And this is actually not easy to do. And most languages actually don't allow to do something like this, even though if they have lambdas. And it's very hard to do it by hand. So Kate Gregory had a talk at the Meeting C++ conference last week in Berlin, and she said that like in most languages, lambdas are easier to use than in C++. But they're also harder to use, right? Because if you run into corner cases like this, in most languages, actually, you're done. You cannot solve this anymore cleanly. But in Lua, it just works out of the box. And the Lua VM actually goes to great length under the hood to make sure that this works. So basically, what you do need to do is the problem is the lifetime of the local count, right? Because as soon as the enable counting function ends, you need to make sure that the count variable still stays along. So what the Lua VM actually does is it keeps track of the lifetime of the local and of all the closures that refer to it, which in this case are two. It's the new print function and it's the function that we return in the end to access the count again. And then when it detects that a local variable is about to go out of scope, but there are still closures that are referring to it, then it actually moves that that value over to the free store. And the closures are able to detect that whether a variable still lives in its original scope or has been moved to the free store. It's a pretty clever mechanism. There's actually a paper on the Lua homepage that explains how to implement this. It's quite interesting. Because of this, that functions can capture state implicitly at any time. That actually means whenever you read the keyword function, you should read that as closure construction, because of this amount of state that might have to be captured by the function. It might need to allocate memory, which might need to be garbage collected later. So there is some potential cost associated with that. So whenever the control flow passes over the function keyword, keep it in mind that it might do something like that. With that, let's move on to the central data structure in Lua, which is tables. So Lua somewhat surprisingly gets by with having only a single type of complex data structure, which is tables, and almost everything in Lua is a table. As soon as you've understood tables, you've basically understood everything about the language. So what is a table? It's basically an associative array, if you're familiar with that term. So what we see here is just the construction of an empty table. It's just there's no elements in there. But you can put elements in there. For example, you can use it like a normal array. If you just like put a sequence of numbers in there, and then you can just access them by their position in that array. But you can also use it as a dictionary, right? So if you use string values as keys, then you can just have like a lookup from a string to any other kind of value. And actually, Lua even goes a step further than that, because in Lua you can actually use any type of value as key or value. So you can map arbitrary values to arbitrary values. You can use functions as keys. You can use other tables as keys if you want. That is, again, this philosophy of Lua. Have a few language concepts, but make them as general as possible so they can be applied to a lot of use cases. Tables also have reference semantics. That means if we do something like this, where we construct like two node tables and then link them together through the next field, that builds us what is basically a singly linked list. So we can do this for a couple of nodes, and then we can jump from one to the next by just doing next, 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 next. As with functions before, whenever a control flow passes over the curly braces, that means that a new table will get constructed, which will end up on the free store probably, and might have to get garbage collected later. And since tables are the only complex data structure in Lua, that means that we have to model everything with it. So if I want to build a complex data type, in this case complex numbers, which consist of a real and an imaginary part, both numbers, then I do that by simply constructing a table with two fields, one under the real key, one under the imaginary key. These are really just like string keys. It's like the string real refers to the value for the real part. But since that is a bit cumbersome to write, as you see in the second line here, Lua allows the syntactic shortcut that you have at the line below. But this is just syntactic sugar. Those lines are otherwise completely equivalent. So whenever you read the table dot something, that means that the something is interpreted as a string key for the table lookup in this case. Now we have records. Let's say we want to have member functions. So I have here a function that calculates the conjugate of a complex number. Remember, tables have reference semantics, so the complex number C that is being passed into this function is being changed by the function. And now to turn that into a member function, I simply create a field inside the table and assign the function to that. And then when I invoke it, like you see here on the last line, that is very similar to what you would find on a lot of C APIs, for example, where you give the this pointer that is implicit in a method function called in C++ explicitly. Right? This is just what happens. But as you can see, we also have some redundancy here now, right? Because the complex on the very left side and the complex inside the parentheses for the function call, this is actually the same table. This is the same object. So there's really no need to write it twice. That's why Lua offers another syntactic sugar construct, which is the colon operator, which pretty much does exactly that. It just takes the table that you invoke the function on and passes it to the function call as the first argument. And that's a very nice way how you can realize member functions without having to model them explicitly in the language somehow. So object construction, we don't have types, right? We just have values. We just have tables that have a certain structure. So whenever we want to create now a complex number table, then we basically need a factory function that creates a table of the appropriate structure. So that's how we would write that. So let's say I've now built two of those complex numbers, and now I want to apply some operation to them, like add them together. How would I do this? I mean, for this I need operator overloading. The way that Lua solves it is with a feature called metatables. And metatables basically means I provide a table that describes how my value behaves in certain contexts. So these metatables, you can create like certain special fields on them, like __ add is one of them. And then in this case, we just provide a function that basically performs the complex addition for us and returns the result as a new complex number. And then in our factory function, we can basically say, okay, like every complex number that we're going to stamp out, we assign this metatable to it. And that now means if then we write this C1 plus C2 that we saw before, it will actually go to the metatable, find this function at this special index __ add, and then that performs the operation. Lua also does this already for a couple of its own types. Metatables actually can be attached to any kind of value, not just tables. So in Lua, for example, this is used for strings to ensure that you can invoke all the functions from the string standard library on string values like this. So as you remember, this colon syntax basically means he's going to look for a find function on the string value, but the string value is not a table, so it does not have any fields. But there is a metatable attached to the string value that actually says, hey, if anyone tries to access fields on you like you are a table, then do this. And that's how they are able to redirect this call to the standard library. Metatables are also extensible, so a few of these special __ something fields are predefined by the language. But if you have a nice idea that you would like to model with metatables, go ahead. Like a metatable is just a table. Just add any kind of field that you feel comfortable with. So one problem in Lua is since these tables are open, it's just associative arrays, is that it's very hard to encapsulate data. So let's say you have a type like a date, where you have like 3 fields, year, month, and day, and they might have complex invariants between these fields, so you don't want to allow direct access to them. The way that you can solve that in Lua is, instead of returning a table with the 3 fields directly, you return a table that simply gives you access through setter and getter functions. I wrote here just the ones for the day, but you get the idea. Then in the factory function, you create a local table that contains the actual data. So this is the associative array with the 3 fields that you can access directly. And then we actually do the same trick as we did before with the counter. We define our getter and setter functions as local functions in here, and they pull in the L self table that contains the actual data into the closure, and that's how they access it. And now, as you notice, what we give out to the user is just a table with 2 functions, And the actual data only lives inside the closure of those functions. So it's perfectly encapsulated. And we don't actually need to introduce something like a private keyword to do this. This just comes naturally from the properties of tables and functions in Lua. So it's quite a neat example of how this design philosophy works in practice. Of course, since all our types are tables, we can perform basic reflection on it, because we just need to inspect the fields, and that tells us basically everything we need to know about the type. In particular, we can iterate over all the fields in the dictionary, and then check okay, what kind of data is in there, what might I be able to do with this. So this is, for example, how you could implement a simple type to tuple conversion. But what about global variables, right? So, okay, I can perform reflection on the fields of a table, but how do I know which values are floating around in my program in the first place, right? Like all the global variables, can I iterate over them as well? And actually I can, because in Lua, global variables are just fields in a special table, which is called _g. So global variables are actually just syntactic sugar for a table lookup in this special table. For example, if we go back to the example for function hooking, I can actually write a function that allows me to install this counting mechanism on any function that I just give, which name I give as a parameter to this function. So as we see here, we again want to enable counting for the print function, and what happens is it will just fetch this original function from the _g table, then do the same trick again with installing the count and saving that function back to the _g entry where the original function lived. And one other thing, so going back to what we said earlier, that if Lua finds a variable that has not been declared before, it will just create a new global variable. This can be harmful. For example, what we see here, I made a stupid typo and now I assigned to foobar instead of foobar. And this would just silently work. And this might actually be a bug, right? So I don't want this. I want Lua to catch this for me. But remember that assigning to global variables is just creating entries in a table. So since _g is just a table, I can assign a metatable to _g that actually forbids it to set new global variables on here. And Lua actually has, the Lua developers actually provide a module that allows you to do just this. And then the idea is basically that you restrict the places in your program where you can declare new global variables. So for example, you could say that you can only create new global variables in certain contexts, or you can only declare them when you go through a special declare function or whatever. And again, this basically comes for free just because we have metatables and from the fact that _g is a table. Okay, so that was a very quick tour of Lua. And now we're actually going to switch over to C++ and take a look at some of the ways how we can integrate Lua with an existing C++ program. So as was mentioned before, Lua is an embedded language. That means your main function still belongs to the enclosing C++ program. Usually Lua programs are not standalone, they are embedded within other programs. And within the main function, usually I start out by creating the Lua state. And this actually encompasses all of the state of the VM. If I create two distinct Lua states, then there's zero overlap between the two. It will be like two completely distinct VMs. I can do I can run them concurrently on separate threads, and there's no overlap. This will just work. And actually, all of the Lua API functions take the state as a first argument. So this is sort of, if you want, this is like the main object in Lua's API if you want to interpret it as an object-oriented API. So once I have the state, I can just run some Lua code on it. Really, that's all there is to it. This is enough to get Hello World running within C++. So now, of course, if I want to embed Lua into C++, I need some interaction between the two. And that means I want to call some of my C functions from within my Lua script. And what I need for that is a wrapper function that has this signature. All functions that have this signature can be exposed inside the Lua VM as functions callable from Lua. And as you might notice, this function actually does not have any arguments or any return values that make sense. It just takes a Lua state and then returns some int, which in this case is actually the number of actual return values. And the reason why this works is that Lua's API is constructed around this concept of a stack. And this stack is actually not the actual called stack as you might have it in the C++ program, but it's somewhat similar. So all of the function arguments and all of the return values go through the stack. And actually, every value that you ever want to get inside the Lua VM or out of the Lua VM has to go through the stack. Okay. And this has two interesting implications. First of all, it means that the number of functions that you need on the API to get values in or out of the VM is rather small, because basically what you need is, we said in the beginning, we have 8 different data types, and you only need one push function and one pop function to get such a value on the stack or off the stack. The second implication, and this is a bit more subtle, but this is actually really powerful, is that in Lua, the stack actually solves the ownership problem for us. Because when interacting with garbage collected languages, you have the problem. If you grab a value from that language, and then the garbage collector runs and sweeps this value away from under you, then you have a dangling reference. So you actually need to somehow make that language aware that you are now holding on to an object of it from basically another universe, from the C++ universe. And doing this can be really cumbersome, but in Lua, because all of the values that you can pull out of the VM have to be on the stack first, you just say, okay, the stack has ownership on a value, and that's it. And that solves the problem. And this is actually really powerful in practice. The downside is that interacting with the stack creates a lot of boilerplate, right? Because like, if you imagine, if you just want to set a value inside a table, you have to get the table on the stack, you have to get the key on the stack, and you have to get the value on the stack, and then you make an additional function call that actually performs the assignment of the value into the table at the key. So this creates a bit of boilerplate, but apart from that, it is actually quite an elegant design. So how do we get stuff on the stack? As I said before, there's basically a push function for every kind of type. I just gave 2 examples here for pushing numbers and strings. Some of the other types are a little more complicated than that, but not much. So now I have these 2 overloads. And now I just write a variadic function that just pushes a number of arguments on the stack. And I don't know how many of you are familiar with this syntax down here, where the push call happens. This is a new feature in C++ 17 called fold expressions. Basically what that means is it will make one push call for each of the arguments in order. And the cool thing about C++ 17 is that the order is actually guaranteed if we do this for the comma operator, even if the comma operator was overloaded, which in this case, fortunately, it's not. But that's a nice addition that we get there. If we don't have C++ 17 yet, we can also do the same thing with the library. This here shows an example for Boost HANA that basically does the same thing. Or if you're really unlucky and you're stuck with an old compiler that cannot even do this, you can also emulate the same thing in C++ 11, but the code is really horrible and I'm not going to explain it. It's just up here for reference, so please don't try to understand it. With that in place, we can now actually get arbitrary. Okay, we can now push values to the stack. Now we also want the other side of the coin, getting values that are on the stack and bring them back into C++. And here we have the fundamental problem that Lua is a dynamically typed language. So the entries on the stack could have any of the 8 basic data types. So at this point, we will need a switch case over the type. But as you notice, the different return values that I construct inside the cases, these are already distinct C++ types now. So once I am past this switch case, I'm in the C++ world, and I want to make use of the type system, of the C++ type system. I want like support for strong types. I don't want this weird Lua, everything is dynamic thing anymore. So the question is now, what is the return value for this function going to be now? Let's just say I have these classes for number and string, and I don't want them to derive from a common base class. I could do that, but people these days don't like to do this anymore for various reasons. They still share a common interface, though. For example, I can at least always get the type of each value. And then a very neat way to solve this in C++ 17 is just to use std variant. Because like variant is like a tagged union, and it works very well if I know all of the different possible types that I want to put in there beforehand. Since in Lua I only have 8 types, I only have to put like the 8 different types in the variant, and that's it. That's a very nice type then to solve my problem. And then I can use visitation to invoke functions on the type. For example, here this would be a visitor to get back the type of the concrete value that I have in my hand at a certain point in time. Another way to do this is if you don't like variant for whatever reason, you can roll your own type erasure. This is I wrote here Sean Parent style because he popularized this in his Inheritance is the base class of all evil talk. I will just go over this really quickly. If you think that this is super confusing, just watch Sean's talk. There was also a talk by Louis Dion at CPPCon this year, which explains all of this in great detail and all of the different options that you have. This is just to give a rough overview. So how does this work? We define a class that basically tells what our interface is going to look like. So in this case, every type is going to have such a type function. And then I provide a template that basically implements this concept for a type T, right? So I can instantiate this model with a type T that has a type member function, but that does not have to derive from the concept class itself. And then this model of T will implement the interface that is specified by concept, and I can invoke it polymorphically when I have a concept pointer, right? And then my value class just looks like this. I have a unique pointer to a concept, so to the interface base class. And I can construct it with any of my concrete value classes, like my number or string. I can put that into the constructor here. And then the type function is just exposed through this concept interface. And the nice thing now is that my number and string classes, they are still unrelated classes. There's no virtual function calls on these classes. So as soon as I know that I have like a concrete number type, I don't pay for virtual function calls, but I still can use them in a polymorphic context if I put them in such a value container. That is in really brief words what this is about. Okay, so now we are actually ready to call a Lua function. So as I said, we need the Lua state for everything. We can get a function by name, and get global will put it on the Lua stack. then we can push all of the arguments to the function call using our pushargs function that we wrote earlier. Then we perform the call. And then we actually have to inspect the Lua stack for the return values. The thing here is that, as we have seen in the beginning, Lua functions can have an arbitrary number of return values. So I actually need to inspect the stack to see like how many return values were pushed on there. I'm not going to show the implementation for that, but I'm sure you get the idea. And now we can call the print function with like a number and a string, and it will print it to the console. And that's it already. So notice that this call function has like the most general syntax that you can think about. Just an arbitrary number of arbitrary return values and an arbitrary number of arbitrary parameters. Usually I want to restrict this as much as possible. So for example, if I know the number of arguments, I could choose a signature like this. If I know also the types of the arguments, then I would restrict it even further. But of course, you might not want to write all of this by hand, right? I mean, it's not that difficult, but hey, there should be a library that already does this. And actually there's several libraries, but one in particular that is quite powerful and quite modern in its feature set. It's called Sol2. You can see the GitHub link at the bottom. So this is a single header-only library. So you can just download the sol.hpp header, include it like this, and then you're good to go. Sol, the central object in Sol is the state view. If you already have an existing Lua state, maybe because there is like an enclosing program that already uses a different framework for interacting with Lua, you can just construct a state view on that. You can also if you're just using Sol, then you can also construct a Sol state, which also takes ownership of the state if you want that. And with that, this is what calling a Lua function would look like. Basically the same example as before. So we can access the state view through the array bracket operator and just give it the key of the value that we want to retrieve from the global environment, in this case the print function. And then this will return a Sol function object, which can be an arbitrary function, and we can just invoke it like here. We could also pull the last two lines together on a single line. This was just to illustrate the return value here. And of course, the Sol function is just a generic function type. It could have any signature, but you can actually convert the Sol function to an std function, which then has a specific signature, and Sol will take care of all of the magic of making that happen. Now, the way that we just saw was actually the easy way, just calling a Lua function from within C++, but where Sol really shines is if we go the other way, if we actually have a C++ function that we want to make callable from within Lua. Because as we saw before, we have to wrap all of our C or C++ functions in this signature where it just returns an int and takes a single Lua state as an argument. And then we have to write by hand all of this boilerplate code that takes care of getting the parameters on the stack and getting the return values again back from the stack. And Sol simplifies this a lot. So let's say I just have a C++ function like here with this signature. And this is actually already a pretty complex function, right? So we see that the last argument is actually untyped. It can be any kind of Lua value, and we even have multiple return values, which are here modeled as returning a tuple. And then in Sol, this just works. I can just say like, please bind this function to the name somefunc in Lua, and then I can just call it from within Lua. So a lot of magic going on behind the scenes here that I don't have to write out. And also, what is quite nice is there's also some magic for going the other way around again. So what you see here is like a full round trip, where I make a function call of a Lua function, which is basically under the hood just a wrapped C function, and then you can see here I get my 3 results back. And I use this syntax from C++ 17, the structured bindings feature. So what this does under the hood is this function call to the Lua function, since the Lua function returns a number of return values. Sol will actually model that as the function returning a tuple. And I now use the structured bindings to get the elements of the tuple as individual variables here. Actually, I could not get this example to compile with the latest version of Sol, but it should work. It might just be a bug in the current release, or it might be a problem with my machine. But this is how it's intended to work. Okay, so wrapping up. This sentence is actually the elevator pitch that the Lua designers give for their language. It's a powerful, efficient, lightweight, embeddable scripting language. And I hope that by now you have at least a rough idea what each of these words is supposed to mean in the context of Lua. I also have a small list of literature. I want to particularly point out the second entry here, which is Programming in Lua. It's a textbook by the authors of Lua explaining how the language works. It's a really nice book. It's quite thin. It's only like 300 pages or so. If you're interested in the language, this is a really good starting point. The reference manual is also quite nice, but the textbook is really amazing. So if you want to start out, have a look at that. And with that, I think we have some time left for questions. So thank you. Any questions? Yeah. Yeah. It's not on.
Okay.
Yeah.
Do you have any experience in running Lua as a kind of a scripting language for some business roles, or maybe administrators that edited business rules in a high performance environment?
So what in particular are you worried about, that it's too slow, or do you want like functionality like from a bash script, or what are you looking for in particular?
I'm looking about systems that perform a lot of transactions and
okay, I see. So Lua has
time critical.
Yeah. So Lua has a reputation for being quite fast for a scripting language, but the important part here is for a scripting language. So if you have a good split between fast functionality that you can implement in C or C++ functions or some other systems programming language, and then just use Lua as a driver for the business logic that calls all of these functions whenever it needs to do some heavy work, then that works, yeah. But you need to do this split. You need to be aware of which parts cost the performance and which part you need to optimize, and then you need to be able to move those to a high performance language. Then that works very well, yeah.
Thank you.
I know maybe it's redundant, but my question is how to ordinary C++ guy needs use Lua language to improve, for example, to improve a program which is writing.
So one fundamental advantage of Lua is that you can reload your scripts on demand. Right, so you don't have to recompile. Whenever you make a change, you can actually, with very little effort, write a framework that detects whenever a Lua script has changed and then automatically reload that and incorporate the changes into your program. If you have something like that that can speed up the development massively, simply because like you don't have this whole recompile cycle that you usually have in C++. So this can be a huge win, but of course this has to pay off, right? So if the project is one where you can benefit from this ability to reiterate really quickly, then this might be a huge win. If your developers are anyway spending most of their time like thinking really hard and then making a small change, recompiling and thinking again for an hour, then not so much.
Yeah, okay, I understand. It's the next question is how to use this language in conjunction with, for example, another scripting language. Is it in compared to, for example, Xhubble or another scripting, for example, Perl or something like that?
Yeah.
Is it slower or faster, or is it not comparable at all?
Well, it depends on your use case, right? So in the end, you have to measure. There exist benchmarks on the internet already where Lua does quite well, better than most scripting languages, but that doesn't mean that it will work good for your use case. So in the end, I'm afraid you will have to measure. Okay, one question over there.
Hello. I see a lot of security issues regarding the executing Lua script at runtime. How it can be handled?
Okay, so
there is some kind of certificate or.
Yeah, that's a good question. So Lua is, so by design, the language is memory safe, right? So if you restrict the environment, like if you don't load, for example, any of the standard library functions in there, then the worst thing that the user can do is like consume a lot of memory or like consume a lot of CPU cycles. But he cannot actually break out of the VM and like read memory regions that is not supposed to, or write somewhere where it's not supposed to. That being said, of course, only given that the Lua implementation itself does not have any bugs. So the implementation is not very big. It does not change a lot compared to a lot of other projects. So you could say that it's proven in use. But of course, if the more critical your use case are, then the more likely you are to need some kind of certification. And as far as I know, Lua does not come with that yet. I could be wrong, but yeah. But by design, it should work. So given that the implementation does not have any bugs, you should be able to set it up in a way that it works for these use cases.
Okay, any other questions? Okay.
Okay.
So, Andrea,
yeah?
You convinced me to the Lua, and I suppose that most of audience also. So I think that you deserve a big applause.
Thank you.